All right, hello everyone. We're starting our last unit here, right? Last unit. Right, so we're talking today about sequences. Right, sequences is kind of just a pattern. Right, so if we look at this first sequence, we have a Fibonacci sequence where we're always adding the previous two terms. So based off that, our next term in this situation, 8 plus 13 would be 21. If we kept going, we got 34. Oh, making little errors here. Right, then our next term would be 55. Right, so you're always adding the previous two terms. Right, a triangular sequence, in that situation, right, is there a common thing being added, a common thing being multiplied? Well, there's things being added, but it's increasing by 1. So the pattern here is a +2, +3, +4 scenario. So we'd have, if we went to our 10th term here, 2, 3, 4, 5, 6, 7, +8 would put us at 36, +9 would put us at 45, +10 puts us at 55. So these are not our normal sequences. These are special scenarios. Our normal ones are going to increase by the same thing, whether it's addition or multiplication. So a sequence is a set of numbers that follows a pattern. Every number is called a term. And we're going to focus on two. We're going to focus on an arithmetic sequence or a geometric sequence. So just getting a really basic idea. T2, what's the second term? In this case, 4. T5, fifth number, 10. T6, 12. So that's just labeling the term in the scenario. All right, an arithmetic sequence. What we see here is we have a constant +3 going on, making our fourth term 12. Now, what this has is that +3, that's called our common difference. The thing that we're going up or down by. The way we find our common difference is, in this situation, it could be T2 minus T1, and we replicate that pattern with T3 minus T2. The fact that we get 6 minus 3 is 3, 9 minus 6 is also 3, shows that we have our common difference. And this is the number that we're constantly adding, to the previous term. So I'm just going to give out the formulas right now. So our 20th term, how do we find that? Our formula for arithmetic to find missing terms is this. Tn equals T1 plus n minus 1 times d. So if I look at this problem, my common difference is 3. I'm looking for my 20th term. So my first term plus n, which is 20, minus 1 times my common difference of 3. 2 plus 19 times 3 equals 59. So with that formula, in words, the nth term equals the first term added to n minus 1 common differences. Right? Since this is going up by a constant rate of 3, a arithmetic ends up being a linear function. If we graphed it, term 1 is 2, term 2 is 3, term 3 is 8. Right, that would be up 3 over 1, up 3 over 1, up 3 over 1. We'd have a constant linear setup with our arithmetic function. Now on the flip side, geometric, right, we are in this case multiplying by 2. Right? We're not linearly increasing. In this situation, we're exponentially increasing. Right? So we're going to have 24, 48, right? We have 96. We're getting larger and larger and larger and larger as we go up. Now, there's not a common difference. Here it's called a common ratio, and that's the thing that gets multiplied to the previous term. Multiplied by the preceding term. Right? And we got a formula. So our formula here is T1 times R to the n minus 1. Right? So T1 is still that first term, R is that common ratio, and n is the spot that we're looking at. So 3 times, R here is times 2, or plus 2, times 2, times 2. All right, so R is our 2. And just like in this previous step, how do we find R? T2 divided by T1 needs to be the exact same thing as T3 divided by 2. In this case, 6 divided by 3, 12 divided by 6 gives us 2. Raised to the 20 minus 1. All right, going to be a super large number here. We type into our calc, 1,572,864. And again, there's how we find our R value. All right, so in this situation, what does this mean? Well, it's the first term multiplied by n minus 1 common ratios. And being that we are drastically increasing, right? It's not going up 2 over 1, up 2 over 1, up 2 over 1. We are going, if we look at this sequence that we set up, this one up 3, up 3, up 6, up 12, up 24. We are increasing. We are exponentially increasing. We'd have an exponential function in that situation. All right, quick check. All right, so if I do, in this case, negative 4 minus 7 is negative 11. Negative 15 minus negative 4 is negative 11. We have an arithmetic. Our common difference here is negative 11. So the 31st term, T1 plus n minus 1 times the common difference, negative 323. All right, so here we got 1/3 divided by a half. Right, that's the same thing as 1/3 times 2. So we get 2/3. Right, validate that one with, I went backwards. T2. Right, then I got 2 over 9 divided by 1/3. Same thing as times 3. That'd be 6 over 9, which also equals 2/3. All right, so yes, we have a common ratio. This is geometric. 1/2 times 2/3 to the 31 minus 1. Super tiny number that your calculator is going to spit out. 502607. All right, what do we got here? 4, negative 2, 1. Negative 2 divided by 4 is negative 1/2. 1 divided by negative 2 is negative 1/2. Geometric with a common ratio of negative 1/2. 4 times negative 1/2 times 31 minus 1 point, even smaller. 1, 2, 3, 4, 5, 6, 7, 8, 37. Right, more complex problems, more complex scenarios. All right, so what term is this? Right, so we know that Tn is 34,816. We don't know n. Right, so we're told it's geometric. So the key thing here is that this is times 2. So our setup here with our geometric formulas, 34,816 equals T1 times your common ratio to the n minus 1. Right, divide by 17. 2,048 equals 2 to the n minus 1. You got options here. One option is we give a log. So if we give a log, now I know a lot of people are groaning, right? But this is actually using logs to be beneficial versus kind of random stuff. If we divide by a log 2, we get n minus 1 equals 11, n equals 12. So this is actually a helpful spot where we use logs. The other option is that if we take this, we could do change of base. Right? 2,040, if I sit there on my calculator, that's 2 to 11 equals 2 to the n minus 1, n equals 12. Doesn't matter which way you do it works best for you. Right? Arithmetic. Right, so what do we got going on here? Plus negative 8. Yeah, you can say minus 8, but understanding that it's always going to be the common difference that we add. So I'm going to say plus negative 8. We got our formula. 17 equals t1 plus n minus 1 times negative 8. I'm going to subtract 305, negative 288 equals n minus 1 times negative 8. Divide by negative 8, positive 36, equals n minus 1, n is 37. That's a little bit of a backwards idea in the situation. Plug in what we have to find what we're missing. All right, I can tell just by looking at it, it's geometric. So our common ratio here, let's see. In this situation, our common ratio is, so 1 divided by negative 1/5 would become negative 5. Negative 1/5 divided by 1 over 25 would become negative 5 also. So our common ratio is negative 5. So negative 1953125 equals 1 over 25, negative 5 to the n minus 1. If I multiply the 25 over, my number gets extremely large in this situation. 488,28125 equals negative 5 to the n minus 1. Now, if I gave a log here, what's the issue? Can't have a negative argument. Logs won't work. Well, okay, so we could make this the change of base, which if we sit there on our calculator and plug in negative 5 to some power, negative 5 to some power, it's going to be 11, giving us n equals 12. All right, so that's if we do change of base. But understand this. If I wanted to, I can make this 1 over 25. If I'd pretended that r was 5, then I'd have 1/5. Then I'd have 1. Then I'd have 5. Here would be negative 5. There would be 25. Here would be positive 25. What I want you to see is that the numbers are basically the same. There's just not this flip-flopping of positive, negative, positive, negative, positive, negative. So being that the numbers are in the same spot, whether they're positive or negative, if we wanted to at this moment, we could just kind of pretend. I'm going to pretend r is 5. I'm going to pretend that my number is positive. All right, so we could pretend it's positive because, as we see, there's, 25 and 25 are in the same spot. 5 and negative 5, 1 and 1, negative 1/5 and 1/5, 1 over 25. So if the r is negative 5, the r is 5, the numbers are in the same spot. We just don't have that flip-flopping back and forth of positive negatives. So if we did logs in this scenario, logs would work, and logs would also give us 12. We would just have to pretend that everything was positive. All right, common difference here, plus 8. 305 equals 17 plus n minus 1 times 8. All right, so I subtract 288 n minus 1 times 8. 36 equals n minus 1. N equals 37. That seemed really similar to the problem above. It's kind of just a backward scenario there. All right, down here. All right, so let's see if I figure things out. I got a common ratio of about 1.06. 2270.6051 equals 17 times 1.06 to the n minus 1. Divide by 17, 133.5650059, 1.06 to the n minus 1. Log of this, n minus 1, log 1.06. Divide that over. And the great thing about this, even with these gross numbers, in the end, when we use our calculator, we get 84. Right? Because with terms always have to be nice, clean numbers. We're never getting term 1.5. We're never getting term negative 2.6. Nice, clean, positive numbers are the terms we're looking for. So even looking at logs, yes, we're still going to get nice, clean, positive numbers. They might be a little off due to rounding, but we're going to go with the actual positive, nice number there.